Good afternoon, everybody. My name is PK Pandey. I'm a partner with the REDI Acoustics, and I'm here today at the AES show with Peter D'Antonio. Let me correct myself, Dr. Peter D'Antonio, the founder of RPG Acoustics. RPG stands for Ray Phase Grading, and the inventor of many acoustic products that we use still today, 40 years later. Peter, welcome.
Thank you, PK.
And Peter wants to talk about some of the new developments that we have at REDI Acoustics, which is basically like an AI type of software that we've written, which is an iterative programming or of the rooms. So go ahead, Peter. Why don't you start?
Thank you. So that's who I am, and I'm Director of Research at REDI Acoustics, which we founded in 2020 with John and PK and a bunch of talented acoustical engineers. And what I'm going to do today is introduce, as PK said, a new app called ROCS, Room Optimizer for Keyboard Spaces, and yes, REDI ROCS. And first, I'm going to go very briefly over a little bit of science, and then we're going to go into the app and show you how the app works. So the thing to remember is that the sound that we perceive in a room is determined or is influenced by series number of factors, beginning with the size of the room, the shape of the room, and then the mass and the stiffness of the room's boundaries, because that determines how much sound is transferred out of the room and how much low frequency is absorbed by resonating surfaces. Then, of course, we have the position of the source, and then the spectral, spatial, and temporal characteristics of the source, and then the position of the listener. And at high frequencies and mid frequencies, we predominantly hear the direct sound, unless it is corrupted by early reflections from the walls, the ceiling, the floor, and the console. As we move to lower frequencies, the room is dominated by modal resonances, the decay of the modes, and reverberation time. So what our goal is to remove all sources of acoustical distortion that you see here, so that we can create a neutral sounding control room, so that the mix does not have any acoustical signature of the room in it, which leads to the slogan that if you can't take the room out of the mix, you can't take the mix out of the room.
Peter, let me ask you.
Yes.
Why is it just low frequencies? Why is it not high frequencies as well that are very difficult to deal with?
High frequencies are a little easier to deal with because the wavelength is much smaller. And so high frequencies are usually dealt with porous absorption to control, like comb filtering. And low frequencies, having such a long wavelength, are difficult to deal with. You have to use wave acoustics.
So it's physics.
It's
basically.
physics.
Yes, it's just physics.
And then the low frequencies, you see the modes developing at low frequency. The challenge, when you think about it, is to find the sweet spot in the room for a given geometry where the speakers can be placed, where the listener can be placed for all frequencies. That's the challenge.
And also how, especially the low frequencies are energizing the room.
Exactly.
Especially over time. It's just when you're listening to music.
Right. And so we optimize 4 metrics. Just very briefly, the frequency response, the blue line, and the, trying to point here, the light blue area is the spatial deviation, and then the decay of the modes, the level of the reflections in the reflection-free zone, so that we don't hear them, they're below thresholds, and then of course the reverberation time. And I'll be talking more about this tomorrow at 2 o'clock and at 4 o'clock. But today we want to really get to the program. So we use a finite element method at the low frequencies, ray tracing, and the image model at higher frequencies. And then we combine the two to form an impulse response, which we can actually oralize in the room. So that's what ray tracing looked like. You send out thousands of rays, and this is what we have to deal with, the finite element method, in which you mesh the room. So the first module that we developed is called the non-cubic iterative room optimizer, or NERO. And what the goal of this module is to simultaneously optimize the room geometry for any shaped room, as well as the position of the loudspeakers and the position of the listener. And that could include the mains, subs, several listening positions.
And I can see that, is it actually doing thousands of iterations here?
Yeah, we're up to 7,000 iterations, because there are many, many possibilities here. But the trick here, now, in the past we used to do this manually, right? You'd have some experience, you'd say, well, this room worked, I'm going to repeat it in the next room. Now we can do it for the first time iteratively, which means to look at many different options, but also to simultaneously optimize all three. And the only way,
So you may have some choices to find the optimal one that's for you.
exactly.
Yeah, interesting.
And so there are thousands of them. And so at the end of the day, we can do this, and the only way we can do this is with a multi-objective search engine. It's an AI, iterative, meaning choice after choice, search engine. So that's the first module. Now the second module is called the treatment optimizer for room acoustics. This is a very, very complex module. Once you determine the geometry of the room and the position of the speakers and listeners, you then find all of the areas within the room that can receive an acoustical treatment. So you have many different depths. You have, probably a deeper area in the back than on the sidewalls and the ceiling. So we have a library of hundreds of acoustical treatments, both porous absorbers, resonators, hybrid resonators that have porous absorption on the face of the resonator. And you're seeing the absorption coefficient down here of all of those possible choices. And what you see on the right is the frequency response, the spatial deviation, the decay of the modes. And you'll see when there's a peak in the steady state frequency response, you'll see that the mode rings. And so you want to get that temporal decay flat, and you want to get the reverberation time within recommended limits by those dashed lines. And again, the only way to simultaneously optimize that is with an intelligent AI search engine.
I find this very interesting. So are you telling me that rather than having to rely on intuition or experience and just making the same room over and over, now we have actual data of where these issues are in the room, and then we're making, you're designing the treatments for each specific issue in the room? Because I see several treatments and I see several waveforms, but I see they're all dealing with the different frequencies here, the peaks. That's very fascinating, because now we have data about where to put them rather than relying on intuition and good luck.
That's an interesting question, because in the past, you may have had experience on something that works, but you never know whether that is the optimal solution. Because we're going to look at thousands of possibilities. And as you'll see in the next slide here, this is essentially the NERO program for non-cuboid spaces. This is restricted to cuboid spaces, which many people at the show here deal with, bedrooms, garages. And so, again, we're looking at thousands of possibilities with the length, the width, and the height of the room, as you'll see. And we're going to simultaneously optimize then the frequency response and the spatial deviation. Spatial deviation just means when you're mixing, if you're in a large control room and you've got racks of gear, you're moving over to change the EQ or what have you. And so you want to be able to hear the same thing with very little variation in what you're hearing. If you're in a small project studio, you're going to be pretty fixed. And so we have all of these options. And what I'm going to show you now is the actual app that we've been developing for the ROCS program.
And ROCS is room optimization for cuboid spaces. Okay.
So
So
there
what are
we have it.
looking? What are we looking at here?
Okay, so this is the actual app, and it consists of three modules. You have the input module, you have the analysis module, and you have the optimization module. So
Okay.
let me go through this.
Oh, I see. So you have tabs here.
Right. So we have 6 variables here. We have the room length, the width, the height, the listener distance from the rear wall. The listener is measured from the rear wall, and you can play with this, and I'll show you why in a minute. Now we're going to do an optimization. So we have to have an accessible area that this variable can move within. So this is 16.4 feet. It can be 3.3 feet smaller or 3.3 feet larger, likewise. And the same thing with all of these. Now you may have a room, so you can vary those, and that's what these buttons are. Now let's say you have a bedroom and you're not going to change the design of your bedroom, so you're going to deactivate those 3.
Right. Those are fixed.
Now down here you have an ear height, so if you're a tall person or a short person, you can adjust it. And then you have a listening area, which is this rectangle here.
Oh, so that's like the sweet spot, basically area of sweet spot.
We're optimizing, in this particular case, we're optimizing 27 points
Yeah.
around in a cube around the sweet spot. And in this particular case, we're going 6 inches on either side, above and below, and front back.
Okay.
Then you have the speaker height. The speaker height is the distance from the floor to the bottom of the speaker cabinet. Then you pick your speaker from a growing library of speaker types. And I just pick one here at random. And now you have to define what type of a boundary you have in your room. Whether it's gypsum, plywood gypsum, like we have in the WSDG studios and commercial studios, or you might have a home studio and you might just have 5/8 drywall.
Yeah, mostly they're going to be gypsum.
Mostly
only.
it's going to be gypsum.
On
And
this
you can have
frame.
concrete or masonry.
Yep.
So now that we have all of those variables, and you can do that in metric or in feet,
Okay.
and then you take a look at the room. And that's what we're looking at here. And to make sure that you have the speaker at the right height for your listening room, in this case, the speaker is a little bit higher. You might want to have it at ear level. You might want to have it higher. And this is the frequency response and the spatial deviation. Spatial deviation that you see down here. Then you can look at the variables. You can actually look at the room and, you can see, now in this case we haven't changed those, so let me look at this again. And when you look at the room variables now,
I see. So it's, yes. You're giving it the delta, the plus or minus
you're giving it the delta
possibilities
in the
of
room.
the room.
And the speaker can vary up and down, and then the angle can change, and the speaker distance to the speaker can also change. So let's say we've done that, and so now, by the way, we have moved from the analysis engine, from the analysis module into the optimization module. But let's just see, I've run these previously, so let's start with this one here. I'm going to load those parameters. Okay, now I'm in the optimization module, and I'm going to just look at, I'm going to view the progress of that optimization. So you have 3 choices. You can do a fast look, a more balanced look. In the fast look, you get 10 generations with 25 evaluations. In the balanced mode, you get 50 observations, and the detail mode goes even beyond that. So what I'm going to show you right now is 2 versions of the fast optimization. So in this particular case, this is the progress of the optimization. Now we're going to look at, we're using a very complicated multi-dimensional, multi-objective search engine. So we've done 10 generations of 25 evaluations.
Oh, and you can look at them all to see what.
We can look at them all by using this bar down here. So this is the first solution. This is the second solution. This is the third solution. You can see the room is not changing. This is the fourth solution, or maybe it is. No, it's not changing. And then this is the last solution. Now, this is what would happen if you could not change the dimensions of your listening room. But you'll notice that even with a given geometry, the position of the loudspeaker and the angle is going to change because there are several locations in this room that have an acceptable performance. Now, if we want to, we can say, well, okay, now I have the option of actually varying my dimensions. So I'm going to load this, and then
let's see.
and
Got
then
a little small, more narrow and smaller.
yeah. And so now we're going to look at. So we've done several more optimizations, generations, I should say, and then we'll look at the optimal solutions. Now in this case, we only have 4, and we can view them here. So in this case, the room is a certain shape. The speaker and listener are placed where they go. In this room, the angle between the speakers has changed. In this room, the geometry of the room has changed. And in this room, it has changed again.
So in essence, we've taken the hundreds, on the fast analysis, we've taken hundreds of generations and distilled it down to 5 choices, which
5
are the
choices.
optimal. And you can choose
Right.
which ones you think.
And then
will
if you
work.
want to look at them, you can say, I'm going to choose the second optimization. And just a second here.
The view selected?
Oh, yeah, Bruce, thank you. And so you see all the parameters. So the length is, now these are metric, and we're not going to go into why that is, but
Yeah.
they will eventually be in imperial. So you see the dimensions of the room, the listener distance, the speaker distance, and the angle. And you can view whichever one you have chosen. If it could be that one, and then you view that one, and you get the dimensions here, and you see the performance. Now, obviously, this is not a flat response, but this is the best that you could do with the geometry and the location of the speakers and the listener. Then you would go into an acoustical module, that Tora module, which we haven't developed for this particular search
Yeah,
engine.
now that you have all this information, now you can design the treatments to deal with all
Exactly.
these.
And so you would,
Optimized.
so you could go, if you went back to the viewing of your room, you could look at all the specular reflections.
Can you just look at the first order? Can you, are these the,
I can't see that far. Can you?
just click on second order? Is that
Second order.
disappear?
So this is this is really instructive because this is telling you where to place porous absorption on the side walls.
Exactly.
to
Yeah, with the XYZ position. Exactly.
The exact positions to where to put your porous absorption.
No mirror necessary for this one. Right?
And if I want to say this, never use thin porous absorption, 4 inches porous absorption,
Yeah.
because if you use thin porous absorption, you're just filtering the reflection. And then this tells you where on the rear wall to place your diffusers, and it tells you where on the ceiling to place your either a cloud or a treatment on the ceiling, and so you pretty much have all the information now to basically evolve the design of your room. And
Great. So that goes back to that previous slide where you had all those treatments in there
yeah,
in your presentation.
in the presentation where we had the Tora engine, where we had 15 treatments in that particular room, and the Tora engine found the optimal treatment for every location in the room. That is, having done this for 40 years, I can't tell you what a godsend that is, really, because how many guesses could you possibly take? You know, you run out of energy after a while. Now we're looking at thousands of possibilities.
Yeah.
So hopefully that improves the quality of the rooms that are being designed now. And obviously WSDG is incorporating all of this technology. And
So it's like you said, it's an APEC. It's in the analog realm, in the reality realm. It's
Right.
dealing with that without having to like an analog parametric EQ.
exactly. So
Look at that.
I mean, the other thing, we've all been we've all been schooled on the importance of dimensional ratios. Like you can go to the internet, and there's hundreds of Excel spreadsheets that tell you this is the length, width, and the height, and this is the ideal dimensional ratio, and blah, blah, blah. It's important, but you have to realize that the position of the speaker determines the modes that are excited, and the position of the listener determines the modes that are heard. So while this is important, it only tells you where the modes are. It doesn't tell you the relative energy. And then you have the initial frequency response. You also have the initial pressure field, which is the pressure in the room. And you'll see how this changes with the different treatments. So, for example, if we went back to,
Can you slide that?
Let's see.
Is that
Where was I here?
pressure?
That's a
pressure
good
field?
question. Yeah. Yeah, it's forming the pressure field. So we're looking at, and there's a frequency indicator somewhere that I can't see. So
Ooh.
as we move up, you see where the nulls are, you see where the high pressure is. Because think of it, this room has got a minefield of high pressure and low pressure areas. And imagine finding the sweet spot in that minefield for the speakers, the listener, at all frequencies. And you can see how that changes. You obviously don't want to be sitting in one of the nulls. I mean, looking back at when I first got into this industry, this is like a light year shift.
Yeah.
So yeah, that was a good suggestion, PK. I haven't played with this maybe as much as you. So
this would be a very valuable tool for acousticians and studio designers
it's a learning tool.
who don't have a giant staff or not using ComSol or not using all this other software or many softwares to try to.
It's an incredible learning tool.
And you've done it for this cuboid space. You've done it in a matter of minutes.
Yeah.
Yeah.
So if you look at, this is one of the optimizations. If you look at the pressure field, it'll be somewhat similar, but this is even after optimizations. It has told you which of those areas is the most beneficial to be living in. Yeah.
Mm-hmm.
So, I don't know, are there any questions or? Yeah.
Well, you can go to the website, put in your dimensions of your room, which is REDI Acoustics.com. Put in your dimensions and sign up, and you'll get this information back.
I do have another question.
Yeah.
Sure, go ahead.
I work in speaker manufacturing. How do we connect to, for example, get you information to have our speakers?
I'll give you my card.
And can I also ask another question?
Yeah.
With with more and more immersive rooms being built,
Right.
I would imagine this just gets crazier and crazier as we would add
Yeah.
speakers to it. Is there
We have been doing the Atmos rooms and the
I mean, the way, when you think about the Atmos room, the way we deal with it, and I'm sure other people have their own opinions, the left, center, right speakers are critical. And that's what we optimize. And then we look at the 6 speakers in the ceiling and see whether they corrupt any of the metrics that we have optimized. And but the one thing that you'll see tomorrow in the Roubaix section is we can optimize multiple subwoofers. Generally the subs underneath the mains are sort of fixed, but we can also optimize them around the room. And what that does is that improves the listening area. Yes.
So it's not so hot.
Right.
Well, I guess the key is knowing exactly where to place those. Otherwise, you just make it worse.
Exactly. It's the same thing with using acoustical treatment. I mean, you can put a resonator in the wrong part of the room where the pressure is not high, and basically create a notch. And so, location, location, location. Right? Exactly. Now, in this library of hundreds of acoustical treatments that I mentioned earlier, we have porous absorbers, we have resonators. All of those surfaces have been measured. I have a 25-foot long impedance tube, which I can measure from 20 hertz to 200 hertz. We have a large reverberation chamber that we can measure from 63 hertz to 5,000 hertz. So when we go through one of these, not here so much, but when we go through the Nero and the Tora engine, all of those surface treatments have been measured.
Okay, so we're vetting everything, making sure it's performing, so we can put it in the design.
Yes.
That's great. We have a couple minutes left, Peter. Is there anything you wanted to add to this? This is fantastic. There's a lot of data here, and you can find a lot more on the website. Just poke around. And we also have, you can go in there and design your own treatments. We have the treatment calculator, which Peter developed many years ago, but we've updated it. And you can, if you have a few weeks of spare time, you can go in there and have some fun.
Yeah, I don't know if I can't really get online without my hotspot, or I'd show you that treatment optimizer, but it's based on the transfer matrix method, which can calculate the impedance. Then from the impedance, you can calculate the absorption coefficient. And best go on the website, and it's free. I mean, you could spend, when you go on vacation, you could go on the website and kill a couple of afternoons.
Fantastic. Peter, thank you so much.
Thank you,
It's great
PK.
to be here at the AES show, WSDG. Thank you so much for giving us the opportunity to speak here. And if you have more questions, go to the website or ask anybody around here. All these people from WSDG are very well versed on REDI Acoustics and what we're doing as well.
It was a pleasure being here. Thank you all for attending.